Hi, we're going to be looking at logarithmic differentiation, which is using logs in order to find a derivative. At any point, if you feel like you need to pause to copy down some notes or anything like that, feel free to do that. But here is the process of logarithmic differentiation. What we're going to do is take the log of both sides, usually the natural log, of both sides of an equation, and then we're going to use the properties of logs to our advantage. We're going to look at 4 situations here. The first example is going to be a very basic example, and you're actually going to see that we don't really need to use it, but you'll see how it works. The second example, we're going to need logarithmic differentiation in order to find the derivative. Then I'll look at one where logarithmic differentiation is useful but not necessary, and then a situation where I would not use logarithmic differentiation. While you're working through the problems, this isn't just about being able to know the process, it's also about deciding when the process is appropriate. You guys know how to find how to find derivatives of many functions, and yet we haven't used logarithmic differentiation before. So while you're looking at your homework or any types of problems, don't just automatically jump to logarithmic differentiation. Make a conscious decision of whether or not you should be using it. So here's our basic example. So I said that logarithmic differentiation was the process of taking the natural log of both sides and then using those properties before I take the derivative. So on the left side I have the natural log of y, and on the right side I'm going to use my properties where I'm allowed to bump that x down in front of the natural log. Haven't taken a derivative yet. Let me actually start to do that. On the left, the natural log's derivative is 1 over u du. And on the right, I have a product, but one of them is just a number. Natural log of 3 is just a number. So the derivative of the right side is just going to be the natural log of 3. Now what I'm trying to solve for in this problem is dy dx. So I'm going to multiply both sides by y. But because I actually know what y is, here's why I know what y is. Look back up here, y equals 3 to the x. I'm not really going to write that dy dx is y natural log of 3. I'm going to write that it's 3 to the x times natural log of 3. Kind of a better format for our answer. So I said this was a basic example, kind of showing you the process. I personally wouldn't really use this every single time. It's a good way to first see the problem though. What I really would use if I wanted to take the derivative would be our rules for exponentials, which was rewrite the function, take the natural log of the base, and the derivative of the exponent. And then you see that we have the exact same answers. So here is actually an example of a situation where I probably would not use logarithmic differentiation. But again, I just want you to see how it works. So let's look at an example where we do need logarithmic differentiation. And the reason that we need this is because we've never talked about finding a derivative when you have a base that involves a variable and an exponent that involves a variable. I know how to solve x to a number, and I know how to solve a number to x for derivatives, but never x to the x. So we're going to use logarithmic differentiation. This is required. Logarithmic differentiation, again, the idea was to take the natural log of both sides and then use the properties. So on the left I have the natural log of y, and I'm going to use the properties of natural logs, which says I'm allowed to bump that exponent down in front of my natural log. I haven't done any calculus here. I've actually done a lot of algebra 2 here. Now I'm going to apply the calculus. Now I'm going to take the derivative of the left side, 1 over y dy dx. And the right side, I am stuck with a product. So let me write sine, and then I'm going to write the natural log's derivative in red here, 1 over u du. And then I'm going to have the natural log, get that in green, and then we'll put the derivative of sine in black, which is cosine. Now again, remember, your goal here is to get everything, or the derivative solved for. So I'm going to kind of clean up all the stuff that I have over here. I'm going to clean this this up as one group, clean this up as another group. Not really a whole lot to clean up on that second part. And so I'm going to end up writing 2x sine of x over x squared plus 1. And I've got, I'm just putting the cosine in front. No particular reason. I just kind of like it better in front of the natural log. I was supposed to multiply both sides by y though. And again, though, I'm not really going to call it y. I'm going to call it what I was told y was equal to, which in this case, once again, is sitting right here. So for my final answer, I'm going to end up writing that dy dx is equal to what I know y equals, times all this. And I really am going to leave my answer that way unless there's something obvious that I could clean up in there. So let's look at a situation where logarithmic differentiation is not required. It's useful though. I could definitely use the quotient rule on this problem where I could bump that denominator up to the -5th power and use the product rule. They're still looking pretty ugly. So here's how logarithmic differentiation will help. Again, I'm taking the log of both sides and then using the properties. And for this, remember, I can take the quotient that I have here, and it's going to be the log of the numerator minus the log of the denominator. But I'm also going to be considering the exponents. Right now, what I would suggest that you do is see if you can expand this out, pause it first, see if you can expand it out, and then see if you have the same expansion that I have. Not necessarily the derivative, but the expansion. Did you get all this? Notice the 1/3 and the 5 in front. There's a subtraction symbol right here in the middle. If you got all that to work out, now in just a second, pause it and see if you can get the derivative and compare your answer to mine. How did you do? I have kind of a messy looking answer, and yes, this is really how I would end up leaving it. I've got this piece in front that's representing y, and it would get multiplied by an entire product, so make sure that you have these so that the function would get distributed, and I've just kind of cleaned it up in there, and I'm really not going to do much else with this answer. Again, remember, this was not a problem where it was necessary, but hopefully you can see with just one step of logs and using the properties of logs, you've avoided a really messy quotient rule. Do you think anyone's going to leave if we just wait a minute? They're going to think that was our bell. All right, let's look at one more problem. This one is a situation where I'd actually not use logarithmic differentiation. Something that would initially make me kind of think about it is the fact that I do have a fraction, and so if I do take the natural log of both sides and I use my properties, I've got a nice situation where I can split up that fraction, and so now I don't have to worry about using the quotient rule anymore. And so I take the derivative of both sides, 1 over u du. I would have another 1 over u du situation, and another 1 over u du situation. And I could go through, move things around, solve for y. This didn't seem too bad because of the fact that I was quickly avoiding the quotient rule, and the derivatives that I used instead were also kind of quick. But the reason I wouldn't use it here is because when I go through this, as I solve for y, and I'm just being too lazy to get down to what dy dx equals, I'm going to have a bunch of things. I'm going to get some common denominators. Because of the fact that these pieces aren't super complicated, I will actually get a common denominator, do some distribution, combine like terms, and the algebra of the simplifying is what's going to take so long. When I could have just used the simplifying idea in the original problem, that I have this entire fraction that gets divided by x, so x squared over x plus 1 over x, or in other words, x plus x to the -1. So the derivative of that isn't going to be too bad. 1 minus x to the -2, or in other words, 1 minus 1 over x squared. So that derivative wasn't so bad either, and I didn't need logarithmic differentiation. So places that I think would be convenient would be when I have a fraction that's super messy. I would not call this fraction super messy. And places where I'm going to need it is when I'm going to have a variable raised to a variable. This is required logarithmic differentiation. So what you should do now is you're going to work on your assignment from your assignment guide. And while you're completing the problems, your first decision is to figure out, do you need logarithmic differentiation or would it help you? I'll warn you, the first few problems, they're not just going to start using logarithmic differentiation. It's a little farther embedded into the work. But be thinking about why you're doing what you're doing. Good luck.